A single rack of the new Blackwell supercomputer weighs roughly 3,000 pounds. It packs 600,000 individual components into a single frame, running so hot it requires liquid coolant pumping through its core just to keep the hardware from melting. This chart tracks the computing power required by modern AI models over the last decade. Historically, the growth was steady, but as systems gained the ability to reason, that demand spiked, jumping to nearly 100 times what engineers expected just 1 year ago. Meeting that demand falls largely on Nvidia and its CEO, Jensen Huang. They are currently scaling a multi-trillion-dollar supply chain to build the physical architecture required to process this volume of math. These installations function as AI factories, industrial-scale systems built for the sole purpose of manufacturing intelligence from raw data. But 30 years ago, Nvidia was a small startup operating in a very different reality. In 1993, the digital world ran on the Central Processing Unit, or CPU. These were general-purpose processors engineered to fetch files and execute instructions in a strict sequential order. One task finishes, the next begins. That sequential design created a bottleneck for the emerging PC gaming industry. Games require millions of pixels to update at the exact same fraction of a second. Pushing them through a CPU one by one caused immediate data congestion, resulting in frozen screens. The math of 3D graphics required a processor capable of calculating thousands of equations simultaneously. Without it, the pursuit of higher fidelity would be halted by the limitations of single-threaded performance. In 1999, Nvidia released a mechanical solution, the Graphics Processing Unit, or GPU. They utilized a concept called parallel computing. Instead of relying on a single, complex CPU core to process data linearly, a GPU divides the work across thousands of smaller cores that execute their calculations at the exact same time. By calculating thousands of pixel geometries concurrently, the GeForce GPU could render an entire 3D world instantly. However, there was a strict limitation. The architecture of this early GPU was hardwired exclusively for graphics processing. Jensen Huang recognized that the exact same parallel structure used to calculate lighting and geometry could solve physics and complex scientific equations if researchers could only access those cores. By 1999, the hardware could resolve the math of 3D gaming, but its 1,000-core architecture remained inaccessible to researchers in other fields. By the mid-2000s, Nvidia spent significant capital to build a bridge between their gaming hardware and the global scientific community. CUDA provided a direct software interface, allowing researchers to program the individual GPU cores for general mathematical operations without translating their work into graphics code. When computer scientists began experimenting with neural networks, computational models designed to process information by weighting connections between nodes, they made a critical discovery. The dense matrix math required to train a neural network perfectly matched the parallel architecture Nvidia had built for gaming. Nvidia built hundreds of specialized software libraries to accelerate specific tasks, ranging from medical imaging analysis to autonomous driving algorithms. The release of CUDA allowed laboratories and tech firms to use consumer graphics cards to run vast mathematical models, making Nvidia's silicon the standard for artificial intelligence research. In the current era, the method of retrieving a stored file and delivering it to a user is being replaced. We have moved toward generative computing. An AI system ingests thousands of variables of context and constantly calculates the probability of the next output, generating what are called tokens. A token is a basic unit of data, like a fragment of a word or a pixel, created in real time to build an original response. Pushing a model to reason through complex problems requires a massive increase in token generation. To maintain speed, companies must link hundreds of thousands of GPUs together over high-speed networks, operating as a single computational engine. Modern server infrastructure functions as an industrial production line where electricity and context enter the system and synthesized intelligence flows out. This physical infrastructure has pushed Nvidia to over $130 billion in annual revenue, operating today as a full-stack hardware, software, and networking provider. Their parallel computing libraries processed millions of environmental variables required by the world's top 30 autonomous vehicle manufacturers. Those identical hardware structures now govern physical AI, where complex reasoning models dictate the physical movements of humanoid robots navigating real-world environments. Nvidia's attempt to resolve the pixel bottleneck of the 1990s inadvertently produced the exact mathematical engine required for modern reasoning. By solving the computing constraints of early graphics, Jensen Huang and Nvidia engineered the hardware necessary for the next stage of human intelligence.